So now we will talk about a power in a balanced system. So if you have a balanced three-phase source having a phase voltages of these values, if they are connected to a balanced load, whether delta or Y, we will get these phase currents. And we all know that V is equivalent to the voltage times the current. So when this is the phase per, if this is the impedance per phase, we have the voltage, the current I. So power is just this voltage right here cross this uh, impedance times the current flowing through that impedance. So by passive sign convention, this is V times I. Now substituting the values for I and A, we will get this value. We'll get this equation right here. Then using the identity and simplifying, we will get the power in a balanced system equivalent to this value, which is 3 times the phase voltage times the phase current times cosine of theta. So this cosine of theta, so this is the, if you have G phase, the magnitude G, angle of theta. So this theta right here depends on the angle of the load or the impedance or load impedance. So this is a load impedance. So the total instantaneous power in a balanced three-phase system is constant, so meaning it is not a function of time. The total power behaves similar to the DC power, and this result is true whether the load is Y or delta connected. So this equation right here is applicable to both Y or delta loads. And the average power per phase is just equivalent to this total power divided by 3. So we have Vp, Ip, cosine of theta. So we have encountered this equation before in EEE132. So if this is the average power per phase, we also have the reactive power per phase. We have QP equivalent to phase voltage times the phase current sine of theta. And the apparent power is equivalent to magnitude of Vp and the magnitude of Ip multiplied by the magnitude of Ip. So the complex power per phase is equivalent to the power per phase plus A times the reactive power per phase, or this is just equivalent to Vp times the conjugate of Ip, where the Vp here and Ip here are complex numbers. So for the total apparent power, for the three-phase apparent power, is equivalent to 3 times Vp Ip. So the total complex power per phase is just 3 times the complex power per phase, so which is equivalent to 3 times Vp times the conjugate of Ip. Another alternative for the total complex power given by these equations right here, this and this. Or we have the total complex power is just equivalent to, this is the total. We have R total plus J U total. This is equivalent to the square root of 3 times the magnitude of VL times IL with angle of theta. So remember that VP, IP, VL, and IL are all RMS values. And this theta right here is the load impedance angle. So this equation right here is applicable to both Y or delta loads. So Y. So notice these two figures right here. So notice the values of VP, VL, IP, and IL for different load connections. So if we have a total complex power equivalent to 3 times the complex power per phase equivalent to 3 times magnitude of phase voltage times magnitude of the phase current. We have the angle of theta. So for Y connected loads, the relationship between VL and VP is this. VL is equivalent to square root of 3 times VP, and IL is just equivalent to I phase. So if you use this equation right here, and we express the phase voltages and phase current, if we express the phase voltage and the phase current into the line voltage and line current, we have VP is just equivalent to VL over square root of 3, and IP is just equivalent to IL at angle of 0. So this becomes square root of 3 VL IL angle of theta. So rationalizing this expression right here, which will become this. Now if we look at the delta connected load, we have the VL and the VP is just equivalent. Now the IL is equivalent to square root of 3 times IP. So this equation now becomes 3 times, so VP is just equal to VL, then we have IP is equivalent to IL over square root of 3 angle of theta. So rationalizing this expression is just the same with this right here, VL IL angle of theta. So that is why this equation right here true for both Y or delta loads. So if we can express the complex power by VL and IL, we can also express the total real power and reactive power by VL and IL. So the total power is equivalent to square root of 3 VL IL cosine theta. The total reactive power equivalent to square root of 3 VL IL sine theta. So let's have this example. Determine the total average power, reactive power, and complex power at the source and at the load. We have a balanced Y to Y configuration with uh, Z-line impedances, which are also equal. So overall, this system is balanced. So we can use the per phase analysis. So per phase. So let's focus on phase A. So this is phase A. AN. We have 5 J2. We have the load per phase. This is 10 plus J8. IAA. So remember, in a Y configuration, the line current is equivalent to the phase current. So solving for IAA is equivalent to, we have VAN over 5 minus 3 J2 plus 10 plus J8 equivalent to, we have 6.81 angle of negative 1.80 amperes. So for a balanced uh, system, we can get the total power by getting only the power of one phase, and we multiply it by 3. So having the value of IAA, can now solve for the total complex power of the source and of the load. So first, let's uh, get the total power, the total complex power at the source. We have PS. So following the passive sign convention, this is negative 3 times Vp, the conjugate of Ip. We have Vp as 110 angle 0 times 6.81 angle of negative 21.8 conjugate. So this is equivalent to negative 2247 with angle of 21.8, or in rectangular form this is negative 2087 plus 834.6. We have VA. So this right here is the total power supplied by the source, and this right here is the total reactive power by the source. Now at the load, to power the load, you can get the value by using the line current or phase current IAA and the uh, load impedance. So we have 3 times the magnitude of IAA squared times the load impedance. We have 3 times 6.81 squared times 10 plus J8 equivalent to 1782 angle of 38.66, or in rectangular form this is 1392 plus J1113 VA. So this right here is the total power absorbed by the load. This right here is the total reactive power by the load.